last talk of the workshop is MCMC Learning. Varun is giving the talk.
Thanks everyone for coming to the last talk, and thanks to Prasad and all the organizers for a wonderful workshop. And as being the last talk of this workshop, I'm going to take the liberty of talking about something that's a lot more speculative than things that you've seen so far in this workshop. So let's see how it goes.
Can you speak up?
Yeah, okay. Okay, so here's an outline of my talk. I'll first very briefly talk about uniform distribution learning and all the nice things that we can do there. And then, unfortunately, if one is interested in learning in practice, the uniform distribution on the Boolean cube is just not a model that people like. And the rest of the talk will try to see how much of this theory we can hopefully use for more interesting classes of distributions. So uniform distribution learning has been around for at least 25, 30 years now. And the idea is there's some target function defined on the Boolean cube coming from some class, and you want to learn this. And there are various models that have been studied for access to the function. So, and here are some classes that sort of in some sense, the richest classes that are known to be learnable in these settings. So for random examples, there's this algorithm by O'Donnell and Savidio for learning monotone decision trees. The random walk model is a richer one where instead of just getting IID random examples, the learning algorithm gets examples from a random walk on the Boolean cube. And under that model, so it's Bishuti, Mosel, O'Donnell, and Savidio who showed that you can learn DNF expressions. In the membership query model, where the learning algorithm can actually ask for a query of each point, what the function value is. So Jackson showed that you can learn DNFs and also richer class, slightly richer class as thresholds of parities. And then the main tool for all of these algorithms is the discrete Fourier analysis, which you've seen a lot in this last week. And also many of these results and other learning algorithms use quite sophisticated results from theory of Boolean functions that we, such as hypercontractivity, the invariance principle, and so on. Right, so there's all this nice theory, but unfortunately, the uniform distribution on the Boolean cube is not a model that is very relevant in practice. And so the question is, do we have to throw out all of this wonderful theory, or at least can we hope to salvage some of it for learning under broader classes of distributions? And the particular class of distributions we look at is distributions that are given by Markov random fields. So what's a Markov random field? It's defined by some graph on n nodes. And each node in this graph is going to be associated with some variable which takes value in some finite set A. Right? And the distribution, so this defines a distribution over the set A to the n, and is given by these functions. So with each clique in the graph, there's a non-negative function associated with it, and the probability. So for any setting of assignments of the variables for each node, you can define a probability that's proportional to this and the product of all the cliques in the graph. So this defines a distribution on some set A to the n. And so what are these models? So these models have been very popular in various fields, such as in machine learning or in computer vision, computational biology, and lots of other fields. And there's also a lot of algorithmic theory around these models. So this theory is for sampling from these distributions. If you're given the description of a Markov random field, how to sample from these. And also in some cases for recovering parameters of the Markov random field and the structure of it. So if you're just given unlabeled data which you think comes from a MRF, can you actually recover the underlying MRF? And there's been a lot of work in this area. But as far as we're aware, there is the question of learning. So if you're given some function that's defined on the domain A to the n, with respect to the distribution generated by some Markov random field, can we learn this function? So this question has not been studied as far as we're aware. And more generally, the question of interest is whether we can actually utilize the structure of this MRF in the learning problem. Because if you can do distribution independent learning, you could do it. But if you can you actually utilize the structure of the MRF to learn things that you wouldn't be able to do otherwise? Let me just briefly outline what the learning model here is. So there's some Markov random field M, and pi is the distribution associated with this Markov random field. And there's some function, unknown target function, defined on the domain that a to the n. Let's say it's a Boolean function. The learning algorithm can get IID examples where, so these examples are drawn from the distribution pi of the MRF. And in addition to this, we'll also assume that the learning algorithm knows this Markov random field in some way. And I'll make it precise on the next slide what we in particular need for the learning algorithm to know with respect to this. In particular, for sampling from Markov's random field, there's a generic algorithm called the Gibbs sampling algorithm, or this is an MCMC algorithm. And here's the description of the algorithm. So you start with any, so this is a Markov chain. You start with any point x in a to the n. And at each step, the Markov chain is going to update only one of the variables in this. It's going to update only one coordinate. And the way it does it is, it picks the coordinate which is going to update uniformly at random, and the new value for that coordinate is picked from the conditional distribution. So fixing all the remaining variables, the conditional distribution on the variable that is going to be changed, it draws a new value from that distribution and then updates the value. And you keep repeating this. So if you run this Markov chain, this has a nice property that the stationary distribution is the MRF distribution itself. And this sampling from the conditional distribution is easy as long as the graph has constant degree. So if the graph has constant degree, then the conditional distribution depends only on a constant number of parameters, and this sampling problem is easy. And we're only interested in the cases. So we'll focus on cases when this Markov chain is actually rapidly mixing as well. Yeah. Poly n. Okay, so before I talk about what we can do with these MRF, let me just mention a couple of Markov random fields that may be familiar to some of you. So the first one is the Ising model. So here again there's a graph, and each edge has associated with it some interaction energy and the configuration of a system. So each variable now just takes values in -1 and +1, and this is Hamiltonian operator, which let's say if we'll only be worried when all the betas are positive. So if adjacent vertices have the same spin, that's preferred to them having opposite spins, and it defines a distribution on this on -1, 1 to the n. And it's known that for as long as these betas are bounded by some parameter which depends on the degree of the graph, the Gibbs Markov chain that I defined on the previous slide is rapidly mixing. That's what's typically known as the high temperature regime. So this is a picture from that. And the low temperature regime, the Gibbs Markov chain doesn't actually mix, and we'll just not worry about that. Okay. So a second example is graph coloring. So again, here you have a graph, and let's assume that the number of colors is much larger than the degree of the graph. The probability distribution is just the uniform distribution over all valid colorings of the graph. And again, in this case, the Gibbs Markov chain is rapidly mixing. So here's just a couple of Markov random fields that some of you might be familiar with. And now let me move on to try and see what we can actually do with them. So let me recall what this scenario was again. So omega, which is a to the n, is our instance space, or the state space. And this is a Gibbs Markov chain associated with the random Markov random field. A nice property of this Gibbs chain, which I didn't mention earlier, is that it's reversible. So if the stationary distribution of it, which is the MRF distribution, is pi, then this holds switch. So the Gibbs Markov chain is reversible. And as a consequence of that, what we know is that if you look at the eigenvectors of the transition matrix, so each eigenvector of the transition matrix is a function from the state space to reals, and all of the eigenvalues are real valued, for one, and the eigenvectors are orthogonal with respect to the stationary distribution. So this actually gives you an orthonormal basis for representing functions defined over to the n. And the obvious question is, can we do some sort of a Fourier analysis using this basis? So at the first sight, this approach seems very naive because, first of all, each of these eigenvectors is in dimensions as some a to the n. And we have no idea how to even find all of these eigenvectors. And even if we could, then we still have to worry about actually finding an expansion of any function in terms of these eigenvectors for learning. And while all of this is true, with being slightly optimistic, we hope that we can hope to tackle at least some of these problems and see what we can do. Okay, so we want to try and extract the eigenvectors of a transition matrix. And what we proposed to do this using the power iteration method for finding eigenvectors. So let me start with some function g defined on the state space, just let's say a Boolean function or even a real valued function maybe. So any function g has an expansion in terms of the eigenvectors of this transition matrix. And what I want to do is try and extract the eigenvectors that are present in g. And okay, so if I multiply g by the tth power of the transition matrix, what I'm going to get is that eventually as t gets larger, the term corresponding to the largest eigenvector is going to dominate. And in particular here, I'm multiplying by this unit vector 1x, which is, again, in a to the n dimensions, it has 1 in the position corresponding to the x, which is just a point in omega, and 0 elsewhere. So this is just, and if I rearrange the term slightly, what I get is this quantity on the left is just the first eigenvector, the value of the first eigenvector at x in g, plus other terms which are hopefully much lower order than we have. So continuing, so what do we get now? So let's look at this expression again. So the quantity 1x times pt is actually nothing but just the distribution on the state space obtained by running the Gibbs Markov chain for t time steps. Right? So if you start the Markov chain at x and run it for t time steps, that's the distribution you get. And so this, when I multiply by x, it's nothing but just the expectation of g with respect to that distribution. And that's something that we can actually hope to estimate because we have access to the Markov chain. And this operator here should look familiar. So this is like the noise sensitivity operator. So if you imagine that you were working with the uniform distribution on the Boolean cube, and you have a standard Markov chain, then this would, depending on the value of t, that controls the rate of noise, and that's exactly the noise sensitivity operator here. So the hope is that you can estimate the LHS by sampling and get some. So let me summarize here. So suppose I have a function g for which I have some compact representation. So I give you a black box or a circuit description of g. And I also have access to the Gibbs Markov, so I can run this Markov chain. Then for any x in the point, we can approximately output the value of the largest eigenvector that appears in g. And g needs to satisfy certain technical conditions, which I won't state explicitly here, but then we can try and repeat this process. So if we do get a handle on the largest eigenvector that's present in G, we can subtract it off and then hope to find the second largest and so on. Of course, because so we don't need to. So we'll get something that's in the direction of the first eigenvector. So we can just normalize and eigenvector corresponding to the largest eigenvalue. Yeah. So the obvious problem here is as long as we're doing sampling using a Markov chain, the error in our estimation is going to be at least inverse polynomial. So it seems hard using this kind of a technique to get any more than a constant number of eigenvectors from any fixed function g. Subtracting out, it will just add up, errors will add up too quickly to get anything more than a constant number of eigenvectors. So far I've not said what this function g is or should be. So I guess one can come up with lots of functions. So here's a candidate function that we thought of, which is, so I fix some subset of the variables, and for those variables I fix any assignment on those variables, and then define this g sub sb, which is just this quantity here, which is the indicator of whether xi actually takes that value minus the probability that xi that takes this value. And again, this function shouldn't be surprising. So if this were the uniform distribution on the Boolean cube, if we were on the Boolean cube, this is exactly the parity function. Right? So this would be a natural place to start with, but you can think of other functions that you could want to use and try and extract eigenvectors from them. And the learning algorithm itself is very simple. So suppose you could come up with these eigenvectors, some collection of them. Now, to estimate what the expansion of the target function is in terms of these, you just need to take dot products, essentially, because you have an orthonormal basis, which is very easy. So these alpha j hats are basically the Fourier coefficients of the target function in terms of these eigenvectors. Right, and what I've said here is this is in some sense like a low degree algorithm, and I'll make precise, a little bit more precise on the next slide. So the part of spectrum that was used here is typically going to be eigenvectors with high eigenvalues, and well, the nice thing is that hopefully these are more likely to capture signal than noise, but it's also mainly just because this part of the spectrum is easier to access. So if your function g that we start with has an eigenvector that has a very low eigenvalue, then it would be very hard to actually use the power iteration method to extract that, because the noise just adds up. And so, for want of having at least one side that says theorem on it, let me write a very informal version of what you can prove. So if you have some Markov random field defined on some state space, and if there is a class of these functions of g, which each function actually needs to satisfy some technical conditions. I have not stated them very technically here, but at least what you need is these functions are bounded, and they have low L1 mass in some sense. So the sum of the absolute values of the coefficients in the eigen expansion of g should be bounded, and you need appropriate gaps in the eigenvalues of the eigenvectors that actually appear in g. So if you have that, then you can extract from each of these g a constant number of eigenvectors. The constant depends on how these conditions are satisfied. And any function that can be approximated using the eigenvectors that you get from this class of function g can be learned using the algorithm on the previous slide. So the algorithm itself is very natural, and the reason I said this is sort of like the low degree algorithm is that if you were indeed in the case that this was the uniform distribution on the Boolean cube, these conditions are indeed satisfied, and you take the standard random walk on the Boolean cube, the conditions that we require are indeed satisfied, and so you can actually just run this algorithm, and it will give you all the lower degree Fourier terms. Right? Now you might say that I'm cheating because I started with these g functions which are already parity. But even if you started with, say, conjunctions or disjunctions of a small number of variables, you'll still actually be able to you'll actually find the parity functions as the correct eigenvectors using this. So in some sense, this is the right generalization of the low degree algorithm to more general fields. Okay. We also did some very, very basic experiments with these on the Ising model and graph coloring. And so what we can think of is for any x, we're essentially expanding on these features which are corresponding to these eigenvectors. And if we only use these features, we do mildly better than just linear regression using the original features. We could also consider what happens if we just construct higher degree versions of these eigenfeatures. Not necessarily, but it turns out that in our experiments we observed that degree 2 regression using these features actually does much better than degree 1 regression, and also just better than polynomial regression with the original variables of degree 2. And we suspect that the reason why this is happening is that these eigenvectors that we find, products of them are in many cases close to being eigenvectors themselves. So in some sense, this higher degree expansion is finding something that's close to more eigenvectors that we didn't originally have. Right. Here's a couple of open questions. So the obvious open question is take your favorite simple Markov random field, favorite simple class of functions. Is there any hope of showing that you can approximate all functions in this class using higher eigenvectors, so eigenvectors corresponding to high eigenvalues under these for this Markov random field? Also, so as I mentioned just on the previous slide, so the auxiliary functions that we were using were these parity functions essentially that depend on a small number of variables. And we suspect that, so G itself depends on small number of variables, and so it feels that because of that, the highest eigenvector in G is also localized in some sense. And this is why maybe the product of eigenvectors are also themselves close to being eigenvectors. The question is, can we understand what's going on here better for general Markov random fields? Here's another simple open question, so if you, so far I talked about Gibbs Markov chain, which had only unlabeled examples that were generated from it. If you do have access to a labeled random walk, can you do anything that you couldn't do earlier? And we can show as under some conditions that the MRF needs to satisfy, you can learn k-juntas by essentially what's a trivial algorithm. They just identify all influential variables. But even that seems to be hard if you only assume that the Gibbs Markov chain is rapidly mixing. You'd need some more conditions.
Can you sort of quantify what do you mean for the first question for a simple model on a simple class of functions? Because just on the hypercube, you could define a Markov chain which essentially leads to higher order parities as the leading eigenvectors, right? I mean, if instead of having high probability of jumping to neighbors, I have a higher probability of jumping to neighbors with even distances and then some distribution, and very small, tiny probability of jumping to neighbors with odd Hamming distance.
Okay, so what I didn't say in these Markov.
So are you sure? Is this because that's the thing about powering? Yeah. So the whole thing you mentioned.
So in the extreme case, if you only jump to evens,
then it's connected.
Yeah, then it's
right,
disconnected. Yeah, so one things that I didn't say explicitly was you want it to be connected and you also want it to be aperiodic,
yeah,
but
sure.
yeah, but
Okay, so it's not clear.
Does it make sense to think about analogs of like query learning models in this kind of setting? Some kind of analog of like Crucial-Mansur finding?
so it's possible. So yeah, we didn't think about it very much. And
Yeah, like the low degree algorithm has some built-in noise tolerance. I mean, is there some notion of noise here that noise tolerance that you've looked at for this model? Like, you're close to some function f on some.
right. So if you're close in the L2 sense, then all of this will hold, I think.
There is an L2 that comes from the distribution of the Markov random field. So all of this, the closeness is the same, right?
So if it's the L2 distance is small in terms of the distribution of the Markov random field, then the same thing will hold.
Okay, I meant more if like the labeling that you're getting are perturbed.
let's do this. That concludes the workshop, and thanks for all coming, and let's thank Simon Institute.